Okay. So I am planning to skip some derivations. Our class will start at 10:40. Nothing to worry. I am planning to skip some derivations. This is my length L. Okay. Let us say my original object was this fellow, and I'm the one who is considering got it. I don't want to color it, otherwise it will become very confusing. So I will skip some derivations. Hello, good morning. So of course, I will have a reaction there. Again, torque. So now I will have shear stress is equal to TR over IP, which your book refers to as TR over J. Okay. Oh, good to see you. I was thinking why you didn't come last time. Then I thought, hello. So let us. Okay, I know you. You are Abdullah, right? Okay. Your name is Hafad. Your name is Ahmed. Your name is
Hazam.
say that again.
Hazam.
Hazam.
Yes.
Did I with starting with an H
Yes.
and ends with M?
No. It's HASUNG.
Okay. Got it. I will remember that. And your name is? Okay, spellings? Tassim. Yeah, now I will remember. And your name is? Baran? Yeah, I remember you. Okay, gentlemen. Life is beautiful. We are back. Okay, so first comment, we will switch gears. So I am skipping some derivations. Okay, so when we are done with the topic, we will see and I will go over the derivations, because usually in all my classes, I always go through the derivations. But right now I am taking some liberty. We will get to the core problem. You will all get comfortable with, solving and understanding the logic. Then we will go through that mathematical drill. Sounds good. And SN, you can hear us, right?
Yeah, Hojam.
Okay. Okay, everyone. So here's the problem statement. Till now, all the stuff we have been doing was normal stresses and not even normal stresses. Let me talk about that. We were talking about axial loading. We were talking about axial loading, right? Let me put a steric here. Axial loading. And just to revise, what exactly were we doing? We had an object and I was subjecting it to stresses, right? forces. So I used to call this P, this is reaction P prime. We used to build our story by talking about what is the, let's say, stress is equal to force per unit area, change in length equal to PL over EA. So all the story that I was talking about was strictly actually axial loading. Probably the fact that I wrote normal stresses is not good. Let me give you a better example. Axial loading. Okay, forget about formulas. My point is we were talking about axial loading. Okay. Now from here onwards, we are talking about torsion. So now I'm talking about, I do not have a circular. Oh yeah, this is circular, but I'm not going to risk this one. Yeah, this one, circular, only circular. Okay. I'm not talking about this one. This is rectangular. I'm talking about a circular object and I'm subjecting it to torsion. Now, this phenomena is technically very important for me, right? Because you have shafts, right? You have shafts that have gears, right? Shaft transmits power. We have gears. Gears are technically putting load, torque on that shaft. So you need to design a shaft. How would you do that if you don't have an understanding of how the torque is affecting that shaft? Are you getting my point? So just imagine like this. This is my hand. I'm putting a torque on this circular object like this. This is torsion. This is torsion, you know, the way I am twisting my hands and I'm trying to change this angle. This is torsion. So from here onwards, we will talk about TORSION, torsion. And I will say that when I do like this, there is a shear stress that this object is subjected to because of the torque I'm putting on it, right? So torque I give, shear stress is induced. That's torsion, right? So shear stress, SHEAR, remember this, okay? STRESS is equal to the torque that I am subjecting this object to, multiply by the radius, we will talk about it, don't worry, divided by the polar moment of inertia, okay? Polar moment of inertia. Now, we will stop here just to get a clear perspective what is happening. So this is your, okay, this is your nice and beautiful, do you see this yellow object? Okay, our in-class students can see as well. This yellow object is my main solid shaft, whatever. I took out a little, you can say I inscribed a circle, I made a mark, okay? Then I tried to twist it. So I am actually observing only this portion. This is not hollow right now, okay? I just put an inscription. The moment I twist anti-clockwise, you see, I drew this pink line. Life was beautiful. The moment I twisted it, this pink line, again, this is highly an exaggeration. This pink line moved to here. Are you getting my point? The only reason I'm making this fancy diagram is for you to understand two different things. This angle that has changed is your phi or phi. You will ask me what is the point of this angle. We will talk about it, okay? The shear strain is different. Look, do you see this orange line and pink line and there is an angle that I have written? That's the change in angle. We have been talking about shear strain, change in angle, change in angle. That's that one. So remember that, okay? Now, if you are saying that this pink line has become this orange line and this angle is my shear strain, what on earth is this phi? That's your angle of twist. Angle of twist. So I am skipping the derivation, but we are not skipping the details. Angle of twist. Done. What is this fellow? Shear strain. I will remove this axial loading. I think you get my point. Till now in this class, this is what I have been doing. I made my point. Okay. Shear strain. Done. Let's go step by step. Now you understand the difference between this gamma and this phi. You have to remember this. Angle of twist is different, shear strain is different. Okay. Now the next point is what's the deal with this R? That's easy to understand. There's a circular object. This one, I am, by the way, Ahsan, can you see me right now?
Yeah, Hajam, I can see you.
Oh, really? Okay. So this is a pen and I am twisting it. Now, if I ask you what is the shear stress, you will immediately ask me at what point from the center are you talking about? So you have to imagine that this is solid, okay? Right now, for now, it's completely solid. One material, life is good. You will ask me, you need to tell me at what point are you asking me the shear stress? Are you telling me to give you the shear stress near the center, or are you asking me to give you the shear stress right at the surface of this pen? Or are you asking me to give you a shear stress at any intermediate point between the center and the outer surface? So this is your question for me, that you are asking us to give you the shear strain. Can you please identify, are you asking me to give you the shear strain? So if this is the center, at this point, hang on, give me, let me use a yellow. This point, this was, it's not even visible now. Okay, this point from the center, or this point, or this point. At which point do you want me to give you the shear stress? Because it's our observation that when I'm twisting, the surface definitely needs to have greater shear stress. That seems reasonable to me. And as I go towards the center for this solid shaft, the shear stress should also decrease, right? If I have just imagine a circular object, consider a foam, big radius, you're twisting. So it makes sense that R will tell me the location. LOCATION. Your textbook might explain to you the R part differently. Radial R, I would say, is the radial distance. Okay. So far, so good. What about? Are you sure? Because okay. What about the polar moment of inertia? Now, polar moment of inertia is, I'm not sure how many remember from their maths classes. I will just give you a very brief. This is we are not getting into pure maths. Remember that polar moment of inertia is actually a summation of your moment of inertia of a section about x and y axis. So just to give you a perspective, how should I explain? This object is rotating about one particular axis, right? And it has definitely a moment of inertia, resistance to motion about one particular axis. You change that, hang on, then this is another axis. So this is the deal, that polar moment of inertia means that if I add both of them, then for the object, it gives me polar moment of inertia. And in a twisting problem, you need polar moment of inertia, not the individual one. And again, I haven't gone through the derivation, but for a circular shaft, I need to give you the polar moment of inertia. You will put that polar moment of inertia, and hang on, let me give you some formulas as well. And because you can ask me, if I have a small radius shaft or a big radius shaft, they all will create a difference. So there needs to be a dependence on the geometry, right? This is a very simple explanation to this. Hang on, polar moment of inertia. Let me give you some formulas. In fact, you can tell me what is polar moment of inertia of a circle. You can Google it. Google it. Huh?
Is there a polar moment of inertia for rectangular objects?
Of course there is. But we don't need that, because this formula is only going to be applicable for circular shafts. When you register for 434 course, then I will go into rectangular and triangular. But this formula, this method only for circular. Pi d power over this 32 and 64 is the only thing I always get confused right from my student days. That's why I asked you. Okay, good. So now I give you the polar moment of inertia of the object as well. Life is beautiful. So one last comment, the angle of twist. Uh, let's talk about one simple thing. I have this pen circular, increase the length, increase the length, increase the length, make it 10 times, make it 10 times. Okay. I stand on one corner, I hold it. So now it's like around 6-7 meters. You stand on the other corner and you just twist a little bit, right? Repeat the experiment. Now we reduce that 5-6 meter length to this length. Again, you hold it from here and I twist. We apply the same torque, right? All of us know that how much, oh come on, what happened? How much it will twist. The 6 meter one will definitely twist more, and this little pen with for the same torque will twist less. So without getting into derivation, which we will do probably in the next class, the angle of twist is TL over GJ. If your object has a small modulus of rigidity, will have a higher phi, high modulus of rigidity, low phi, greater torque, more twist, less torque, less twist. What's the deal with the J? If I have J is IP, right? Polar moment of inertia. If I have low dia, then I will have low polar moment of inertia or J. If I have low dia or low IP, I will have more twist, the angle of twist. For an object with a greater dia, makes sense. Are you getting my point, everyone? Oh, okay. So how many formulas did I tell you? One. Okay. Your book uses J. I use J and IP. For this course, I keep using J, but I'm more comfortable with IP, polar moment of inertia. So if I keep saying IP, you remember J is what your textbook refers to. Where is the other one? 2. Boom. There is another thing that I need to mention, because you have to follow your textbook, and the moment you open your textbook, you will be like, what's happening? You need to tell me the formula for T max. It will be T over IP. This R was location from the center, right? So let me make this is your R, right? When I am talking about maximum, it will happen at the radius of the object. So R is the radial distance. Now I am talking about radius. So let's use the radius as rho. Okay. One more comment I want to make here is, because I am afraid you will get confused. That comment is that, hang on for a second, please. Your textbook uses, instead of radius, TR over IP. TR over IP. Yes. Instead of the word R, your textbook uses C. So if you open Beer-Johnston and you see shear stress is equal to TC over IP, you don't get confused. C is the R, the radial location. Polar moment of inertia is J. IP seems more reasonable. If I ask you what is the radius of this object, you will tell me the radius, which is the rho. Is everyone with me? Rho is the radius, R is the radial location. Okay, life is hang on for a second. No, hang on. I just need to make sure that I haven't switched the sorry. Hang on. Sorry. I think this your textbook uses as rho, and your textbook uses where did I write the rho? Yeah, this one, C. Yeah. My apologies, but again, you have to open Beer-Johnston. So one little comment I will write in English that rho is the radial location and C is the radius in Beer-Johnston. Beer-Johnston. Beer-Johnston textbook. I was like, something wrong is happening. I think I have corrected myself and life is again beautiful. Okay, should we do some problems? But before I do some problems, there are further comments I want to make. Should I go to the next slide? We have any student who is still writing. Okay, the comment I want to make is, let me make a circular and you have to tell me what is going on. So this is, why don't you color it as well? Okay, coloring is again something I really don't like, standing here. Then in the name of perfection, you will see I will take a lot of time as well. So this is my center, life is beautiful. This is my, okay, here comes the $1 million question. Why don't you all tell me? No, this is an important question. That's why I refer to it as, why don't you all tell me what will be the plot of shear stress? So shear stress is equal to, what was the formula? TR over IP. And I want to write like Beer-Johnston, so T rho over J. Okay, TR over IP. Okay, so here is my rho and here is my shear stress. And this is my C or radius. So I think it's linear. Nahin? Yes.
Shouldn't be exponential because no, it's
Linear because J is okay. J is, what was that? Pi d4 over 32. I have to double check, by the way. Okay, now I will go for like this. Boom. Right, boom. So let's now make some nice beautiful arrows. Boom, boom. So my whole point of first telling you the concept is, if I had started derivation, mathematical, you would be like, oh, what is happening? But now when I do derivation, probably next class or I don't know when, at least all of you will have an idea what is happening. Okay, agreed? Disagreed?
For this graph, we said that the shear stress will be linear, proportional to the radius, right?
But this is a pure twisting problem. Pure twisting problem. That's it. Every time you see the formula, start to twist the pens like this.
Why it's linear?
Oh, why? Because no, because torque is a constant at a particular section at a particular time. The radial location is a constant, like I don't know, we are talking about this location or this location. Polar moment of inertia for a particular section, for a particular object, for a particular solid object, constant. So this rho is a constant at one location, but you keep on increasing, it keeps on increasing. This equation is y is equal to mx. Boom. Okay, everyone. Why don't you tell me one more thing? Okay, this is a tricky question. We will use our imagination. Let's see who answers it first. Of course, without looking at the textbook. Let's see if I have this one as hollow. Now, make this thing in mind. We are only covering the circular sections. This twisting problem, we are tackling only circular ones. This formula in its present shape only tackles the circular ones. Square, triangular, rectangular, you try to twist 434. We talk about those details there. Okay, here comes the question for all of you. Tell me the plot. Tell me the plot. Now, you cannot make the plot, by the way, because I did not give you one information, and you have to tell me that information. Google polar moment of inertia for hollow circular object. Yes, good. How did you figure, by the way? Observation? Good. Well, that was a good observation, by the way. But he's right, actually. No harm in double checking, but yeah, no. Yes, he's right. Pi by 32 d2 power 4 minus d1 power 4. Now, your textbook writes this as, I don't know actually. So d is r by 2. No, sorry, 2r and 2 2s are 4, 4 2s are 8, 8 2s are 16. So your textbook writes it as, why don't you all double check for me? Pi by 2, radius is c2 power 4 minus c1 power 4. If dia is 2 times radius, does this make sense? Yes. Okay, by the way, in an exam, I have seen most students make this mistake, so I am pointing it out. In a pressure situation, you have to find the radius, and students keep using the dia, so don't do that. Okay, I will go back and I will mention here that you can write it as pi. What was that now? C 2. Sure. Okay, everyone. So the question for everyone is, now give me a plot. Okay, make a plot and show me the plot. Of course, I will make it. I'm just, I just want everyone to be curious. Yes, please.
In the hollow part, the stress is 0. And
of course,
when it goes to the
good
field part, it's going
linear.
Yeah.
Good. So it will be non-zero on the inner surface as well as the outer surface. Unlike this fellow, where shear stress was 0 right at the center, you will have, I will explain. You will have something like this, but you will have to remove this line, and then you will, as he rightly pointed out, no. In fact, we will continue this for our own, convenience. But then I will remove this. Then I will, oh come on, I still messed up. So let's do it one more time. Hopefully one last time. Done. Now I will connect this blue line with this one, and boom. Correct. Then I will connect this with this, and we are back in business. Now all you have to do is just first connect lots and lots of blue lines, and we will start our first example of the day. Done? Done. Yes, no. So orange line is a goner. Oh, sorry, I think I have made mistake. This will vanish as he mentioned, and yes. Now it makes sense. So of course, in a hollow section, you don't have anything. So that's why you have to remove that. Now you can even make a nice, beautiful linear line. Make sense? So now you get my point. It was linear going right to the center, but center does not have any material. So far, so good. Okay. So here comes the first problem of our torsion problems. Let us do it. I have an object. Please tell me if you want me to go back. Okay, no, yes, no. Okay, so here is the nice and beautiful circular shaft. Okay, like this. And it is connected in this rather cantilever formation, whatever. And I have the face of it, nice and beautiful. These are like fresher problems, so you will find them, well, they are so easy, but we will make them exponentially difficult. This is a hollow shaft. I did a horrible job, by the way. But anyways, the question says that if fellow is 1.5 meter long and it has an inner dia of nice and beautiful 40 millimeter, and it has an outer dia of 60 millimeter, boom, tell me for an maximum shear stress of 120 megapascal, what do you think? What is the torque that this object needs to be subjected to if I do not want to exceed the maximum shear stress of 120 megapascals? Well, this seems to be an easy problem. You're doing it. So Ehsan is also doing with us, right? Okay. Ehsan, why don't you also tell me the answer after a few minutes? No, you have to remove the center because there is no material from the center, and you also need a piece of paper to solve this. You have to remove this center.
I'm just asking questions.
No, sorry, they represent the shear stress. So shear stress is but this is hollow, you have to remove this. So shear stress is less on the inner surface, more on the outer surface. Increasing. Definitely. Inner dia is 40 millimeter and outer dia is 60 millimeter. Gentlemen, ID is inner dia and OD is outer dia. Full motor pressure formula, do you remember? Everyone? I think finding polar moment of inertia is the hardest part in these problems with that power force. We get what?
For the shear stress,
No, that the formula is T, what was that, R, which your textbook used at rho, TR over I. So shear stress is depending on torque, but then it's your angle of twist that is depending on the material. You tell me.
12,250.
How much?
12,000.
Right, it's around 4,000. 4,084 exact. So, okay, let me at least start the problem. How did you do it? Number one, J equal to pi by 2. what was that formula now? C 2 power 4 or C1 power 4? That's again C2. Yeah, whatever. C2 power 4. You open your textbook. I won't be surprised if he uses 1 minus 2. But anyway, it doesn't matter. Then it is 5 by 2. Okay, what is this? 30? 30 by 1000 minus. I am telling you, in a pressure situation, this divided by 2 is something that everyone forgets. So please don't do these mistakes. And what was that? Okay. What is J, everyone? Okay. Can anyone tell me the J? Is it 1.02?
So then why didn't we use why didn't we work radius?
Oh, you can. You are right. Yeah, whatever you are comfortable. 1.02 into 10 power minus 6.
Yes, sir.
Sure. Okay. Meter power 4. And then shear stress is equal to, hang on, maximum. Sorry, maximum. So I will do a tau max. I will do a torque. Then I will do a rho. Then I will do a, now not rho. Now talk C. Who said that? Such a good response. You said that. Very nice. Thank you. Then I will do a divided by. Then I will do a nice and beautiful J. And torque comes out to be 120 into 10 power 6 pascals. Oh, come on. Okay, into 1.02. Come on. Into 10 power minus 6 meter power 4 divided by C. Now what is C? C was, oh, what is the value of C? Huh? 30? How did you figure? Because we are talking about maximum shear stress, so it has to be the outer surface. Did you get that point? If you are talking about maximum shear stress, has to be the outer one, not the inner one. So he's right, 30. Very nice, by the way. 30 by 1000. So torque comes out to be, okay, you have to double check, by the way. Is everyone getting 4.08 or not? Kilonewton meter. Sure?
So when we are within torque minimum, then are we going to get final radius?
You mean, oh, but yeah, but the way questions are formulated, the limiting or what do you say? Something of concern is the maximum shear stress, right? Something of concern. If I am designing an object, I would design it for this maximum shear stress, how much load it would be subjected to. Minimum shear stress is not something that is of concern to me, but I get your point. That if, let's say, somebody had told me minimum shear stress that the object exhibits at a particular torque is this value, then tell us what that torque is. Okay, one more question before I proceed. Yes, please.
I couldn't get it to part this T equals that part. Why we divide by the 30 divided?
Oh, yes, because I wanted torque. So I took this J there and I took this here. And when I took the C in the denominator, I asked all of them, should I take 20 or should I take 30?
So it's like T times C, right?
Huh.
Now I get like T at C when you put it.
Right.
Shaman, how is this raised to power 4 then come down as raised to power 2?
Huh?
That C4 and then under that C 30 raised to power 2.
It's mistake, I think. It's my mistake. But when you gave me when I wrote 1.0 into 10 power minus 6, I wrote the right answer. Sorry, this is power 4. It's my mistake. Thanks for pointing out. Thank you. I need to double check. One of the students said it looks like T at C. Did I? No. Oh, okay. This is T multiplied by C, everyone. Okay. Sorry for that. If it confuses, T C divided by. Okay. Okay, in fact, I will answer your question like this. Good question, by the way. His question was, so I will answer his question. Find the minimum shear stress now. It will be, it is hollow. So the inner surface will exhibit a non-zero value. So what will be the minimum shear stress?
You're gonna use
So give me the value. Find it. Find it. I need an answer. So when you using a knife, when you cut a section, the torque is the same on the section. Are you getting my point? So if I'm using a knife and I cut it and I want to see the torque, let's say somebody tells me I'm twisting, right? So I have to cut from a particular section, right? Quite a few torques are acting. I use a knife, I cut from here and I throw this portion away. So the torque is the same on the complete section. That's why the T value will be the same when you're using for one particular section. So here, whatever torque you have found, you use the same for finding minimum shear stress. Give me the value. How much? 80?
6,122.
Minimum shear stress? No, 80 megapascal. I'm talking about minimum shear stress. It will be T, R will be 20 over 1000 over polar moment of inertia is 1.02 into 10 power minus 6 meter power 4. Instead of torque, I told you, of course, like, come on, like you're cutting one section. So what was the value? 4 point. So 0. I think one of the students said 4086, I think, right? So I will take 4086. Give me the value. 80. Good. I will keep on making problem, but we have to move on. What is the shear stress? Let's say at 20, 30, 25. You know the drill. Can you also can find the shear stress at 25 millimeter from the center, right?
Yes.
How would you do that? 25 millimeter from center means T R over IP. Torque, I know. Now R value I will substitute 25. Okay. Yes.
So we writing that T tau equals torque times radius divided by J, right?
But that is but that is maximum. Yeah. But if I am not talking about maximum, then I will remove this.
Okay.
And instead of this C, I will put a R. So R or rho is radial location.
Radial location, right? So J will be the total moment of inertia of the particle, not the section of the particle, right?
No, polar moment of inertia. Got it. Polar moment of inertia is polar moment of inertia. When I am finding it, I will use C1, C2, C. I will not be playing with my polar moment of inertia.
You're looking at whole chunk, right? Not looking at the red part in the first slide.
Because when the object you are subjecting it to some sort of torque, the whole object together wants to resist it. The whole section wants to resist. Okay, everyone, I think I need to proceed because everyone understands this. So why don't you all do another problem? And you are doing it. If we were not in a hybrid, I would have made this a quiz, by the way. So please do this quickly. Give me the right answer. Nice and beautiful. Okay. The question says that I have, hang on. Someone is twisting like this. Of course, static equilibrium. Okay. Boom. Torque. The question says that if this fellow is 8 feet and the C is, oh, come on, I just don't like this C that the author uses, but what was that C? C was radius, yes, 2.24 inches. And the question says, hang on, this is solid. Okay. And tau, oh, come on, tau allow is equal to 12. So you have to say this word so that I know that everyone knows what KSI is. KSI, what is KSI? No, this is tau. So,
1,000 pounds per inch square.
good. No, this is shear stress. So it is KSI is kilo pound per square inch. It's stress. It's a shear stress. What are the units? Kilo pound per square inch. What he said, 1,000 pounds per square inch. Okay. The question says you need to tell me the maximum torque that you can subject this object to. But of course, if the shear stress allowable is 12 kilo pound per square inch, then you definitely don't want to exceed a particular torque. So why don't you tell me how would you do this problem? Okay, let's go step by step. Find the polar moment of inertia and tell me the values. Hang on, and you will give me the values in inches.
Seems radius, right?
Yes, again something that I always forget. C is radius. Yes. Who said that? Okay. Ehsan, are you with us?
Yeah, Hojam, I'm with you.
Okay, so why don't you also tell me the polar moment of inertia of this object? Yes, no worries. Sorry. So what do you do? So instead of this multiply and remove the create from
9.5 also for, right? This question was
Good, good.
9.55. We got it, right?
9.55, you got it, right?
Yes, we got it.
Good. Done? Okay, I think everyone got it. So finish it. So I have nice and beautiful 12 into 1000. Yeah, this was the question. Kilo pound per square inch, pound per square inch. Okay. I multiplied with 1000 T max. Okay. Now, what is the value of rho or radius that you want to substitute? Of course, you are talking about the maximum shear stress. Maximum shear stress has to be from the farthest from the center. That will be the total radius, the C, right? C over J. And what was the value of J, by the way? 39.4. 5 or 4? 5. Okay. I don't know. Inch power 4. And just so that all of our students are on the same page, J is pi by 2 C power 4. Okay. Which is equal to pi by 2.24 power 4, 39.5 inch power 4. Now, instead of this C, I will substitute 2.24 inch and I get beautiful value of tau max as inch cancels with this 4 becomes 3 and you finally get something in pound inches. Give me the answer.
211.88 times 10
211. Good. 211 kilo pounds inches. Keep in kilo pound inches. This is just, these are very funny units, by the way. Anyways.
Now what will be 212?
Quite possible because of some error. I don't know. My note says 211. Sorry, what?
If you use the exact value of the.
I get 212?
Yeah.
Okay.
What is the rule like? Do we have to write it in 3 significant figures?
I will explain the rule when the right time comes. Okay. Now, just to be clear, should I proceed? Do we have anyone who couldn't do this? Are you sure? Okay. Just because everyone is understanding, that doesn't mean that you need to hesitate to stop.
Tau means the tau maximum, right?
What?
The tau.
Tau allowable, of course. Allowable means maximum shear stress that the object can exhibit is 12 kilo-pound per square inch. So of course that would be corresponding to the maximum torque that you can subject it to. And that also means that we will have to deal with the outer surface because maximum shear stress
at the outer surface.
Okay. Sorry, mouse is not working. Yeah, what did you say? 212 or 211 kilo-pound. Okay, hang on. This one was rho. I use R for the radius of the object. I don't think I told you any symbol. Book uses C, we uses C. We use C, okay? Okay. By the way, why don't you do the same problem again? Why don't you tell me? This is funny. We have to do this problem again. same shaft. Okay. And by same shaft, I mean same shaft weight. Same shaft weight, which means, and torque in any case is the same shaft weight and length. But this time with outer dia as 6 inches. So what I'm trying to indicate is everything is the same, just make it hollow. Make the shaft hollow. So hang on. Everything same, make the outer dia 6 inches. And what was the torque? No. Now for the same question, T allowable, everything, you give me please give me 1 minute. Give me torque. Now I understand your question that inner dia is not given. So you have to find inner dia. So same shaft weight and length. So what I am saying is that if the weight is the same, material is the same, then density equal to mass over volume. So mass is equal to density into volume. Then let's say density 1 into volume 1 equal to density of the second case, volume of the second case. So if the length and this is same, so density cancels and you will have actually area 1 equal to area 2. So was I clear on this or not? Understand? You did not? So volume 1 means that you do a control. Instead of volume 1, do A1 L1 equal to A2 L2. Did I say length is the same? Oh, okay. So lengths cancel. So what you do is find the area using C equal to 2.24. Equate that area with the hollow one. Find the inner radius and then give me the torque.
Now what's C in this? Like the inner diameter of what?
Of this hollow. What C?
1.57 inches.
1.57?
No.
I think it's 2, no?
Yeah.
2? Okay. No, you did not understand.
What was the question? Also ask you again.
I was asking like what is C at this part? Like the inner the radius of this.
No. For the second part, how much was C?
So C 2.24 is
2.24 is from previous call.
we have to go
Look, do this. What are you doing?
Pi multiply by 2.24 power 2. That will give you the area of the solid object. Of the whole of this question. Equate this to pi C2 power 2 minus C1 power 2, and with the C2 now I gave you as C2. I will
So we're supposed to find the inner torque, right?
we have to find the inner radius. So 6, 5, 4, 3, 2, 1 pi. This is my part 2. Okay, please do not be confused. I will start again. Pi C2 power 2 minus C1 power 2 equal to pi 2.24 power 2 Nahin, hang on. Are you sure? Okay, yes. C is radius. So we have C2 is 3. Okay, thank you. C2 is 3. So I will have minus C1 power 2 equal to 2.24 power 2. And C1 is?
1.996.
Yes, 1.996. Thank you. Now, please find the torque. Determine. Determine is such a nice word. Determine max torque for what was tau max? Oh, come on. I forgot. Tau allowable is 12 kilopound per square inch. Agreed? No. Formula of area. Okay, thank you. I will. His question is why we have C2 power 2. The answer to his question is because if I have a hollow circular fellow, and if I ask you, you have to give me this area, right? How would you find it? Pi C2 pi r square. So pi r2 square minus pi r1 square, nahi? I am telling you, your textbook uses the, I think, 1 for outer and 2 for inner. But anyways, when you go through your book and solve the problems, you will understand. Is this part clear or no? Because what I did is I said, now instead of a solid shaft, I have a hollow shaft with every single thing is the same. With the only difference that now I'm telling you the density is the same, the length is the same. But the only thing I have, if the density is the same, the weight is the same, I think. Weight is the same. So, absolutely. What did you say? 408 kilopound inches. Yes. Very nice. So he said, I will answer it like this. T, what was that? Let me use a color. Shear stress is equal to T max R over IP. So come on, T tau max J over C gives me torque max, and I will put nice and beautiful T max equal to 12 into 1000 pound per square inches multiplied by the nice and beautiful J. Did I even find J? Oh, come on, I did not. J is pi by 2, correct? C2 power 2 minus C1 power 2. Okay, this is this is where mistakes happen. Okay, what is the value of J? 100? 102 inch power 4, and I get, hang on everyone, multiply by, oh come on, what is C now? What is C? 3. How did you figure? Thank you. Good. Divided by I'm taking too much time. I understand because I'm not sure. Sorry, here there will be a J. Sorry. J is 102. And this is C is 3. This one. This one. Who said that? I'm seeing this one. Oh, sorry. Why C3? Because they gave me that this is 3. 6 inches was the outer dia. Look. Outer dia is 6 inches. And this is 2 inches that you found. So, inch power 4. Okay. What is the tau max? 408. Kilo pound inches. Boom.
What was the answer for this?
What was the answer for?
Of the question before.
The part 1. 212. 211 or 212 kilo pound per 212 kilo pound inches.
Why do we use 3 inches other than on slab?
In which case?
We're finding a maximum 43.
Yeah, here.
Why not 2.24?
Because somebody said the allowable shear stress is 12 kilo pound per square inch. Allowable means the maximum. So the maximum would be exhibited on the outer surface or on a location that is farthest away from the center.
I get that photo, but
No,
we can see like outermost. Like the
Huh?
radius.
sorry.
We use 2.24 inches as C, which is the outermost one because it's the radius, right? And
No,
it's
no,
very
no.
confusing, but now you say it's 3 inches,
Okay, I will explain.
which is also the outermost one, right?
No, I will explain. Look, this was solid. So the C is 2.24. Right now we have converted, we have made another shaft. This time we have made it hollow. In this hollow shaft, I figured out that 3 inches is the outer radius and the 2 inches is the inner radius. Now, if someone tells me the allowable shear stress is 12 kilo pound per square inch, I will follow the same strategy of going farthest from the center. Here, the farthest from the center is 2.24. And here, the farthest from the center is 3 inches. No worries.
Can you go back to the previous slide?
I will.
So there is this torque arrow, like on the front side of the cylinder. It's in the anti-clockwise direction, and in the back side it's in the clockwise direction.
So,
Like, how does this make sense?
because if I am holding the left side by my hand, and I am from this side, you are trying to twist it anti-clockwise. From that side you are holding it. That's okay. This side you are twisting it anti-clockwise. So the reaction will automatically be clockwise. That's why this is in static equilibrium. So you remove the support, and this time from our hand, even if we put a clock in the other side, that would make sense. Hanji. Break?
Maybe a short break.
Yes. So let's meet at 11:50. Huh? Okay. Let's meet at 11. Let's meet at 11:55. That's fine. But by the way, in your break, you can look at our. We have these stairs and we have this railing, right? So you can see bearing stress and shear stresses. You can observe them. Okay.
Question. So could you open the first slide, hocam? Yes. So we said that the torque is constant and the polar moment of inertia is constant for this shear stress, right? So we are not looking at the chunks moment, polar moment of inertia.
We are talking
We are
about
not
the whole
looking
object.
at that. We're talking about the whole, the yellow one, right?
100%.
So when we examine the red part, we're just looking at the radius of it, right? Not looking at its.
100%.
Okay.
100%. The polar moment of inertia of the object, because when you are twisting the object, the whole object as one entity wants to resist.
Wants to
So that's
resist.
why the polar moment of inertia of the whole object comes into the picture. So
So-
you find, for example, in an exam, if I ask you to give me the shear stresses in one solid shaft at 3 locations, polar moment of inertia you will find only one time, depending on whatever total radius it has. It will be those other row values that you will keep on changing.
So I was gonna ask actually the smart, very similar question. So we drew like a graph kind of thing, where it's linear motion, where there's like upward arrows like this one.
Yes,
So this means that every point we can find the shear stress which is
Absolutely.
induced by the torsion force, torsion force, and for every value it will change, right? For every point.
for every
That's what we mean by drawing like specific.
for every point, the shear stress value will be different.
Will differ, yeah? Okay.
And it
But
will-
torque will be same
of
and the
course,
moment
no,
of.
I will explain. Look, if you are holding this object and you're twisting it from this side, okay? Let's say you ask me to give you the shear stresses on this section, right? So what you will do, you will
Imagine
cut
cut
it,
it,
you will cut it and you will throw this part away. Or you will cut it and you will throw this part away.
Okay.
Now, then when
You
you
have
have
cross
cut it,
section.
so on that cross section, you have one torque. It's more like if I am pulling this and if I ask you, give me the normal stress on this section, what you will do is you will cut it and you will throw this chunk away. You will put a reaction, and let's say I'm pulling it with 5 Newton. On this section, you will put 5 Newton. On one section, there is one force. Similarly, if you're twisting on when you slice it on one section that I'm seeing, the circular chunk, I'm just seeing one torque on it. It's just that one torque on different points on that section is giving me different shear
Yeah,
stresses.
that depends on the location of the diameter and stuff like
Good.
that.
And also the torque's direction is parallel to the rotation of x, right? In vector, like
I got your question.
Yeah,
Your question is,
r cross f, it gives the torque will be in the rotation of axis, right?
I understood. Yes, so we are talking about, exactly, I understand your question. Yes, you're talking about that we are putting the torsion like this. So
So the vector of the torque will be in that direction, right?
I understand your question. 100%. This is a very simple case we are talking about.
Okay. Okay, hocam. Thank you so much.
Yes, Hassan, how are you? Okay, so how much late it was, the assignment?
The deadline was given on Saturday.
So the O2 class could not accept the homework. So because I also give an additional 24-hour submission time. So let's say if a student is 23 hours late, the O2 class actually automatically accepts it. If someone is more than 23 hours late, that's when the problem starts. So
I sent it through, and then I decided to send it through make to 8 grade tone worked 3 section.
yesterday was Monday, right?
Huh?
Yesterday was Monday or Tuesday?
Tuesday.
Oh, 206 and 206 deadline was on Sunday. Deadline was on Sunday or Monday?
Homework 2, you mean?
The deadline of the homework that you're talking about. Huh?
It was on Saturday.
It was like it.
Yeah, but the solutions of homework to haven't been announced on a TÜK class.
Huh?
The solutions of
Were not posted.
yeah.
Okay, so-
I actually started solving them. But since I haven't not known how to
Just remove this here. Okay. Where are we? Let us finish this. Why don't you do one problem for me quickly? But before that, just one remark that if you, this is your Tom Max and this is your, let's say C2, and let's say you keep on increasing your C1, then you will have a plot like this. So this means that if you keep on making the hollow shaft thinner and thinner, then no, so I apologize, Tom Min. I apologize, Tom Min. Then the hollow shaft theoretically should be able to sustain the minimum. No, right now I'm talking about, look, let me explain what I'm trying to do here. So maximum shear stress is something that is of concern to you, right? We are worried about maximum shear stress. What else is a deciding factor for me? I really want to reduce the weight. If I have a solid shaft and I have a hollow shaft, the hollow shaft has low weight. But my point is that if I have a hollow shaft and maximum shear stress is determined by the outer surface, what if I keep on increasing the radius, keep on increasing the inner radius? So technically, on the inner surface, you have your minimum shear stress. So as long as your maximum shear stress is within the bound, the minimum shear stress will also be within the bound. So you keep on increasing the inner radius, you keep on making it thinner and thinner and thinner. So the point is you will keep on making it thinner and the allowable shear stress will not exceed. All you are doing is you're just increasing the inner radius. But at one point, it will become so thin, like a Coca-Cola can. It will just wrap and wiggle, and it's not even it's not even practical anymore. So if you keep on making the hollow shaft thinner and thinner, then the hollow shaft theoretically should be able to sustain the shear stresses on the inner surface I have to talk a little loud because of our online hybrid mode. Anyways, to sustain the shear stress on the inner surface, but it would be Coca-Cola can. Now, of course, not Coca-Cola can. You just understand what I'm trying to say, Coca-Cola can. So imagine a Coca-Cola can. The whole allowable shear stress discussion is out of now the park, because now you have other phenomena that are happening. It's wrapping. It's because it's so thin. In fact, you can go back to our discussions. Maximum torque that the hollow shaft can sustain is 408 kilo-pound-inches, and maximum torque that this fellow could sustain was 212 kilo-pound. Wow. Here the outer radius was 2.24, and here the I'm sorry, the radius was 2.24, and now the radius is 3 inches. So wow, you can see that hollow shaft with a very little increase in radius and less weight has a lot to offer to me. Something to think about. Do this problem and we will call it a day. Life is beautiful. There is one topic that we are skipping, by the way, and you may want to go over it, but we have to cover this semester, but not right now. That one topic is temperature changes. Related to temperature changes, when you are going through statically indeterminate structures in your Beer-Johnston, you will see that. Forgot the name of the topic. It is related to temperature changes. So we will cover it in a few weeks, or probably in a couple of weeks. If you want to cover it, you might want to go through it. I don't want to skip that topic. Okay. This is a gear. So we are, what do you say? We are, this is a gear. Something is happening, by the way. This is another gear. This is, you know, okay, there is another fellow. By the way, how many of you are actually going through book reading? Please go through book reading. It is so important. There is a reason I made that Google Drive. And what did you say? Okay, we have this fellow as solid. Book reading is so important. Solid. This fellow is hollow. Tube. Let's call it tube, okay? Otherwise, hollow is a nice English word. Solid shaft again. This is your gears. Nice and beautiful. I'm not going to name all of them. You understand this. Then I will say this is 0.9 meter. Your statics. You have gone through something like this in statics, right? It has been years since I even taught a statics course. Do they cover torques? No, torques. They do, right? Yeah. Okay. 0.9 meter, 0.7 meter. Then you have nice and beautiful 0.5 meter. And the question says that if you have an anti-clockwise, let me use yellow color because our color is working good today. Anti-clockwise, this torque is clockwise. This is anti-clockwise torque. This is anti-clockwise torque. I think you understand. I will remove this. Okay. The question says that if you have 120 millimeter outer dia, hang on for a second, please. 100 and let me use 120 millimeter outer dia. You have 90 millimeter inner dia. Done. For the tube, you have to find if the allowable in the solid shaft, this is going to be one tricky question, is 65 boom megapascals. Then why don't you tell me determine is such a nice word. Determine give me the dia of the solid. Also give me the maximum shear stress in the tube. Okay, first you have to look into whether I missed any details or not. Anything I did not give you. 0.9, 0.7, 0.5. A, B, C, D. Okay. Anything else? Anything else, everyone? No? Yes. This is our shaft. Okay, I will make a free body diagram for you, but I am not doing this problem. You will do it. I am telling you 100%. So this is my nice and beautiful free body diagram. Like this, correct? Like this, and 1, 2, 3, and then like this, correct? And okay, I think I'm. Wait. There is one thing I did not tell you. You cannot even start this problem. That's my mistake. There is a 6 kilonewton meter written here. I had that feeling that I'm missing something. There is definitely a 14 kilonewton meter written here. How can you do this problem, Morgan? You don't know. There is a 26 kilonewton meter, nice and beautiful. And there is a nice and beautiful 6. Okay, and I will call it as TA, TB, TC, TD, TA, TB, TC, TD. 0.9, 0.7, 0.5 meter. Use your imagination, do this problem. Ask me a question. What happened? No, they're the same. They are the same. They are the same. This question is, there are two solid shafts. The answer is yes, and they are same. So yes. So solid shafts are the same. There and there. It's not like this solid shaft is different than this one. Yes, please.
Once you know the shear stress
Uh-huh.
or solid,
Uh-huh.
it's like, for example, we have a graph like this. And
Uh-huh.
for example, we,
Good,
I
good.
think
So this means,
point like this, but the long rule is like this. But we are acting in small point here, the solution,
I will tell you, I understand your question. So it will start from here, the shear stress lines keep on increasing
Mhm.
for a particular torque. This means that the maximum shear stress that the object can sustain is this value.
Mhm.
So of course, the way you will do is you really want to have torque is already fixed. So the only thing that you want to play with is the diameter. You really don't want a big dia because if your torque is fixed, you have a certain value.
We don't know
Yeah.
the solid diameter, okay.
If you have, let's say, a big dia, then
Moment of
नहीं.
inertia will be
big dia,
increased.
नहीं, then you are right. No, you have polar moment of inertia. So you have to find the dia. I cannot say a big dia or small dia because you have polar moment in the denominator. Yes, what is the question?
This rod,
This one, there are two of them. Okay, so there are few students who are getting confused with the rod. This is solid.
and the other.
We will talk. Solid.
Yes.
Both of them are solid, and then this one is, let me use a different color. This is tube, hollow. Yes, what is the answer?
0.0004.
I think this is from your book. Okay. Actually, I don't have the answer. Okay, now I gave him the paper, so let me double check the answers. I think it's 78. What answer do you have? Huh, 70 millimeter. I think so. Okay, let's do the question together. So let's go step by step, okay? How would we start the problem? Answers are secondary. You got it? That's nice. How did you got it? How did you get it? Thank you. Okay, so I will do it. You tell me how you also did it. So we are on the same page. So number one thing is you make cut. Let me use this color for the cuts, the purple one. You cut it. Now that you have made a cut, I will do a shear stress in the shaft AB portion is equal to which torque am I looking at? TA only, right? You cut, you throw the chunk, you look at it from here. So it will be TA. So my reaction will only be TA. What was that? R. I think for solid shaft, I don't know. So let's call it as my
D divided by 2.
C AB. No? D divided by? Yes, C AB.
You can say that DAB divided by 2.
Nice. Yeah, that's fine. But CAB is the same thing, and I will multiply with the 2 only. Divided by polar moment of inertia, which is pi. Oh, come on, what was that? Pi by 2 CAB power 4. Then I have 65. Oh, come on. Okay. Are we proceeding? I think we are proceeding in the right way, right? Okay. What is tau AB? 65 into 10 power 6 pascals equal to, the torque A is given to me as 6 into 1000 Newton meter multiplied by CAB that I really want to find, divided by, pi by 2 CAB power 4. This will become 3. This will cancel. And CAB comes out to be, I think we have a couple of students who did that. 38? You got 38.9 millimeter as radius, right? Okay, 38.9 he got. 38.9 into 10 power minus 3 meter.
Why did we take the torque as 6 kilometers per hour? What did we want? Why did we take the torque as 6 kilometers per hour?
Oh yeah, because my purple line is here. Look, I cut it and I throw the right chunk away. Now when I'm looking at it, I have this one load.
You said it's solid, right?
Which one?
The solid.
No, solid is solid. Solid is solid. Okay, so we have the next cut. Let me use a next cut. This one. Now I have the BC T. What is the maximum here now? It is C2, right? Because it is hollow. Did we used to name one as inner and two as outer, right? Okay, C2 divided by J or IP. Okay, let's try to follow our book for now. J. Okay, so torque BC maximum allowable is, hang on, no. For solid it is given. For this one, it's not even given to me. I have to find the torque max. So I will say I will find it, no problem. What is the torque? In the BC, I cut it, I throw the chunk away. It is how many? 26 and 20. Good. So 20 into 10 power 3 into, what was the 60? How did you figure? 60. Good. 60 divided by polar moment of inertia. Okay, this is the part you need to tell me. Pi by 2 C2 power 4 minus C1 power 4. Can I just write down the value, by the way, everyone? So 13.92 into 10 power minus 6 meter power 4, just so that our students don't get confused. This is pi by 2 into 60 over 1000 power 4 or 2 minus 45 over 1000. Done. Okay, so maximum shear stress. You see, this is how it's dangerous. We need to keep on repeating shear stress. Okay, the torque is the T. It comes out to be 86.2 megapascals. Okay, last but not least, I will talk about, you have to be careful. Now your discussion is not over. There are two solids. You cannot say CAB as this. You have to double check. So for this solid, I will repeat the process. Oh, hang on. If I make a cut, here, I can throw this all chunk away. I only have 6. Right? Is everyone with me on this?
Yes.
Okay. Or there are students who are saying, if we make a cut and we throw this chunk away, then there is 6 and 14, 20, and you have 26, you have 6. So Okay, so I think I can write here equal to CD. Yes, no. Boom. And what you can do is you can put anti-clockwise here. So the reaction here is clockwise. The reaction here is clockwise. The reaction here is anti-clockwise. But that's fine. That's shear stress. Anti-clockwise, clockwise, torque, whatever, that's shear stress, right? Is this part clear where I said anti-clockwise reaction, torque, clockwise doesn't matter because it's a shear stress. And just to be extra meticulous, you can say that TA reaction, let's say, is clockwise. Let's say your reaction is, I think it's pretty obvious and everyone would be like, why are you even doing it? So let's say this is anti-clockwise, this is my clockwise, plus TA equal to 0, TAR equal to TA, and that's why I substituted this here. And then I did the same thing for minus T, TAB, I mean, TABR. Then minus TBCR plus TA plus TB equal to 0. And I got TBC R equal to TA plus TB. And that's why I substituted here 20. That's why I substituted here 20. And AB, BC, CD. I will again put, let's say I make a cut from here. Let's say I put clockwise here. So I will have a minus CD reaction equal to, now I will start to look at 6 plus I have 14 minus 26. And I get TCDR reaction as minus, hang on, 20 minus 6, minus 6, right? Okay, which means that, yeah, I know that everyone already knows this. So this means that it is actually anti-clockwise, but that doesn't matter, positive, negative. It's maximum shear stress. So that's why all of these are clockwise. This is clockwise. This is coming out to be clockwise. This is clockwise. And this value is coming out to be clockwise. But this fellow is anti-clockwise. I think the problem ended like 6 minutes back. I was just being a little ridiculous. Is this clear? Yes, cut it is going to cut it with right. Look, the reason I went through this drill, which everyone was finding pretty trivial, like why are you telling us which reaction is anti-clockwise and which is clockwise, is when next time we come, although we can do it right now, I can just tell you, why don't you tell me the total angle of twist for AD? So essentially you have torques, right? So technically these shafts are twisting. Technically these shafts are twisting, right? So do you remember any angle of twist formula that we went over in this class? TL over GJ, right? So just remember these formulas. Change in length is PL over EA. Twist is TL over GJ.
There is a tube in the BC part.
Right.
Shouldn't it supposed to affect the
Of course.
moment of first polar moment?
Of course. So what you will do is you will have the total twist AD is equal to the twisting that happens between AB plus BC plus CD, because our rules of the game that we have set are the same. Whenever you see a change, you incorporate that in your cutting and everything. So you first find the phi of AB, that will be TAB, LAB over G, JAB. Then you find the phi BC, we will do next time. For phi BC, you will do TBC, LBC divided by G, JBC. Then you will do a phi for CD and you will add them together. Now here here is where 90% problem happens. Torque. Now you have to be careful which torque, reaction torque is in which direction. In shear stress, we couldn't care less. Yeah, that's fine. Anti-clockwise, torque, clockwise. But in twisting, it matters. You get my point? Huh? So that's why I went through this drill of you cut, and that's how you go step by step. Do you have any questions for me? Anyone? Yes.
Can objects experience stress when they are not in static equilibrium?
Oh yeah, of course. We have dynamic stresses. We have an object that is rotating at a very high shaft that is rotating at ridiculously high RPM. At one point it will break, but that dynamic stress analysis is definitely not, we will be talking about here. Probably in your first course of design of machinery, they will talk about those dynamic stresses. Yeah.
Could you open the first slide, Hocam?
First.
Yes, Hocam. We show the wide angle of twist in just one part. In the other part, is there any angle of twist? Like in right section, there's an angle of twist, and is there another angle of twist in opposite direction?
Got it. I understood your question.
It will be same with the angle
Uh-huh.
of twist, right?
Got it,
Because
got it.
it's like this, yeah.
Got it.
So it like
Got it, got it. I understood your question. So actually I made a reference point. I had to make a reference point, that's why. Otherwise, technically, if you are twisting, so for this, there is a reference point here, it twists. For this, it has a reference point. So of course,
so it will like
uh,
this kind of.
uh, uh, it will be what? What is your answer?
I'm saying it should be crossing at the center and just like having, we are having the.
Okay. I understood your question. We will talk about it next time. Okay. Any specific comments? Your midterm exams, I think are announced. Not on CET, but I got the dates, so should be available to you in one day. I will send you an email. Thank you.
Thank you so much, Hocam.
Supriya. Okay, Ehsan, is Ehsan with us? Okay, Ehsan, thank you.
Which topic?
Okay, Hocam.
For what? For your exam?
Upcoming victim.
I have to write an email. I have to sit down. There will be a complete email that I will be sending you. I cannot decide. Yes.
Hocam, the time is
Yes.
determined for
Midterm exam?
yeah.
Oh yeah, but I will send you an email. I have it in an email.
Okay.
I will post it.
Okay, Hocam. Okay, thank you so much. Very nice to Hocam.
Okay, everyone. Thank you.
Hocam, I have a question about the last line.
I have to pause the recording. Then